Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn about generative adversarial networks with TensorFlow and Keras. Now, generative adversarial networks are used to generate data. We can't always count on having data, but we might have an existing data set. So our purpose for using these networks is to be able to generate data from an existing data set. Now, in this particular tutorial, we will focus on deep convolutional generative adversarial networks, or DC GANs as we call them, because we're going to generate images of handwritten digits from the MNIST data set. So GANs work like this. You have two separate neural networks. One is called the generator, and the other is called the discriminator. Now, the job of the generator, that network, is the one that tries to create pictures that look real from an existing image data set. And then the discriminator's job, what it does is to tell them apart, tell real images from the training data set, image set, from the ones that are being generated by the generator, and tell them apart. Now, during training, the generator progressively becomes better at creating images that look real by learning the features in these images, while the discriminator becomes better at telling them apart. This process reaches equilibrium when the discriminator can no longer distinguish real images from fakes. And that's exactly what we want. So here's just an illustration of how it works. So at first, the generator will still not have learned all the features in these images. So it might just be some random output of pixel intensity values and some like a noise type of image. And then many attempts later, it will start getting better picking up these features until it's able to generate images that look real, that even for us humans, it's hard to tell them apart, if we can tell them apart at all. And then the discriminator, initially, it just knows very, very easily that, okay, this is not a real image, it's a fake image, and it's still good at that. But then eventually, when the generator gets really good, and it has learned the features of images and how to generate them, the discriminator can no longer tell them apart. So discriminator might look at a fake image, meaning an image generated by the generator, and it will just classify it as real. And that's exactly what we want. And that way we'll be able to generate more data. So this is very good, very innovative kind of network developed by and discovered by Ian Goodfellow. So now, again, we'll be using the MNIST data set here for this tutorial. And as we said before, we will start with just kind of noise, random pixel intensity values, and then the generator will get better at learning and generating these handwritten digits, MNIST. So the first step is to import TensorFlow and other libraries. So we go ahead and do that. And then we also want to install image.io to generate GIFs and to help us with these animations and showing images. And here you can see just importing some of these libraries that we're going to use. Here, one of the main ones here that we want is TensorFlow Keras. So from TensorFlow.Keras import layers, because we want to use the Keras layers to build our sequential models. And that's what we're going to use. Here we're going to use the Keras sequential API to create these neural networks. So the next step now is to load and prepare the data set. So here we're going to use tf.keras.datasets.mnist.load_data function, and here we're going to store them in these tuples here. So we have our train images and our train labels, and test images and test labels. But we're really only going to use the train images and the train labels. So here we are going to create a variable called train images. And we're just going to assign it a reshaping of our train images that we had before. So train images.reshape, and then we want to reshape them. So initially we have the batch size. So we have 60,000 MNIST images, and they're 28 by 28, and they are grayscale, as we saw. So only one color channel. So we want to actually reshape them to the batch size, height and width, and then the grayscale channel, which is 1. And then the type is uint8, and we want to change that casted to float32. So that's what we're doing it here. And as another step here, we also want to normalize the images from -1 to 1. So we have that. Now we also want to define two hyperparameters here, our buffer size and our batch size. And we're going to create our train data set now. So we're going to call tf.data.dataset dot from tensor slices. So we're going to pass in our train images that we had before, transformed, reshaped, and normalized. And then we're going to call shuffle on them, passing our buffer size parameter, and then call batch on that, passing in our batch size parameter. So this will essentially generate a batched data set, which we are going to use for training. Now the next step is to create the models. And again, we're using the Keras sequential API to create these models. So the first model we're going to create is the generator. And now here we're going to use upsampling, so reverse convolution, using tf.keras.layers.conv2d transpose. So it's essentially the process of convolution as we do in a convolutional neural network, but in reverse. So we call transpose convolution. So instead of starting with an image and getting feature maps and then downsampling the image, we're going to go the opposite way. We're going to start with activation maps and then come the other way until we end up with just one image of the right shape, which is what we want. So here we create a model variable and we assign it to a tf.keras.sequential model. And now we're going to call the add method on that model instance. And for a parameter here, we're going to pass in a layer. So we imported the TensorFlow Keras layers here. So we're going to grab a dense layer here. And there's a lot of hyperparameters here that we're setting arbitrarily, so you can play around with that. But this is just for simple illustration for generative adversarial networks. So we pass in here 7 by 7 by 256 for the number of neurons in this dense layer, and we're not going to use bias here for these examples. And then for the input shape, because this is the first layer in the network, so this is the only time when you pass in this input shape parameter in our dense layer, and we're just going to use 100, just 100 pixel intensity values, which are going to be noise initially, and then from there we're going to generate images. Learn to generate them. So now we're going to add another layer, batch normalization. This is really just to increase stability of our network, just to make sure that between batches and on a per layer basis, the outputs of the layers are normalized so just so we have more of a stable neural network and those outputs between those layers don't vary that much. That's batch normalization. And we also want to add an activation function, obviously, so after batch norm on this layer, and we're going to use leaky ReLU. This is just, we normally would use ReLU, but we want to use leaky ReLU just so we have better training. We don't want to transform negative outputs to 0. We still want to keep information on them. So just a little bit better than just regular ReLU. So we have that to start off with. And now we want to add a reshape layer here because we have a dense layer, which is like a linear layer that is just all of these 7 by 7 by 256 all together. So we want to actually break it up into 7 by 7 by 256. So we have more of a we have a tensor shape here. So we have a reshape layer that we add to our model, and we're going to just do some assert statements to make sure that we have the shape that we want. So we're going to assert if the output shape of our model is none, which corresponds to the batch size. So none for now, and then 77256. And then, so here we want to add a conv2d transpose layer from TensorFlow Keras. And again, this is like convolution conv2d, but going the opposite way because we want to generate images. So we pass in the activation maps here, or the feature maps of 128. And then this is our filters, 5 by 5 filter matrix, or convolution filters, and then the stride, just how much we're shifting as we pass this 5 by 5 kernel over the images. And then padding, we have padding here. So valid means no padding, and same means we do have one padding. So here we want padding because we don't want to lose information on the edges of our image. We want to include that as much as we can. So we're going to go ahead and include padding, which by default will add 0 padding on our images. And again, we're not using bias. So we add that to our model, then we assert to make sure that we have the shape that we want. So this will be the output activation maps. Here are the output feature maps for this layer, 128. And because we use stride 1 and 1 and we use padding, the shape should stay the same here. So 7 by 7. So none, 7, 7, 128. That's what we want. So now, and again, we're working our way to make it smaller until we have this shape, 28, 28, and 1, which is the images that we're trying to generate. So now we're going to, again, add batch normalization in leaky ReLU, pretty standard, same as before. And let's add another conv2d transpose layer. And we want to shrink it again by half, the output maps, the activation maps. And then we're still using padding, but now the strides we're going to double it here, make it instead of 1 by 1, we want to make the stride here 2 by 2. And now that'll cause the output to actually double. So 7 and 7, the height and width 7 and 7 is going to go to 14 by 14, and this 64 will still be 64. So same thing, batch normalization, leaky ReLU from TensorFlow Keras layers, add to our model, and then we'll do our last conv2D transpose here, so we can actually get back to 1, because we just have one image corresponding to this grayscale image, and then again strides 2 and 2, and just we're using the same convolution filter shape here, 5 by 5 with padding, and that way we end up with the output shape that we want, which is none for the batch size right now, and then 28, 28, and 1, which is the MNIST digit image shape that we actually want. And we just return our model. So that's our function called make generator model, and that's going to create our sequential model for the generator to generate our images. So now let's actually go ahead and create an instance. So let's create a generator variable and assign it to this function. So it's going to return a model, which is what we want, our sequential model. And now we're going to create a noise input here. So create a noise variable and assign it to a tf.random.normal. So we're going to sample random values from a normal distribution with this shape. So just one, basically batch size of 1, so just one image, and then with 100 values, pixel intensity values. So that's what it corresponds to. And again, initially it's just a dense layer, and then we'll reshape it from there. But that's the input shape for our generator. So now we're going to run the forward pass for our generator neural network. So our generator, we'll just call it, it's a callable network. So we just call it by passing in the input here, which is the noise, so the input. And then we set training to false, because we're not actually doing training right now, and we'll show the generated image. And with matplotlib. So as you can see, very nice, it generates images 28 by 28 with just one color channel, grayscale, which is what we want. But right now, because the model hasn't been trained, it's just random noise. But it'll get better and better as we run training to generate handwritten MNIST digits. So once that we have the generator, now we want the discriminator, which is going to just tell these images apart. It's going to be essentially a CNN image classifier. So just a standard convolutional neural network image classifier, and that is going to classify images as either being fake or being real. And the idea is that the discriminator will get to a point where it won't be able to tell between real and fake images. And now we have a system, a model, particularly the generator, that is generating data for us, that is high quality, that is what we want, that we can't tell apart from real. So we create a function called make discriminator model here. And again, Keras sequential API, so tf.keras.sequential. And then we're going to add layers. So this is a very simple CNN model as we've seen before. So TensorFlow.keras.layers, conv2D, and we just pass the activation maps or the feature maps here that we want as output. And again, the convolution filter, convolution kernel, and then the stride. Padding, again, we still want padding, and we want the input shape. So the input shape here in this case is 28, 28, and 1, because these are the images that we're trying to classify. So we want here some activation function, leaky ReLU still. Let's add some dropout as regularization. Why not? And a lot of these hyperparameters and including the network architecture you can change and tune, but this is just so we learn in this tutorial how to use this. And we're going to add another one here, and we want 128 instead of 64 as outputs, and same thing, padding, strides, convolution kernels, leaky ReLU, dropout for regularization. And then because this is a convolutional neural network, we actually want to flatten our output here. And so that's going to basically flatten our tensor into a vector. And now at the end, we just want just a dense layer with just one neuron, and that's basically going to output. It's going to be a binary classification problem where it's going to output whether it's yes or no, whether it's fake or real, the image that we're passing in. And then we just return the model. So let's go ahead and create an instance of our discriminator, make discriminator model function here. And so we have an instance here, and then on our forward pass, we're just, as a callable, we're just going to pass the generated image. So we generated an image here, right, with our generator, and we're just going to pass that image into our discriminator, because that's what it's going to look at to classify. And the output we just store in a variable called decision, and we just go ahead and print that decision. So, and as you see, it said TensorFlow, it's a tensor, tf.tensor, and it's really just a single value of type float32. So now so we're using the discriminator to classify these images, and the model will be trained to output positive values for real images and negative values for fake images. So here's really just kind of a random output because it hasn't been trained either. So let's go ahead and define our loss and optimizers. So we want loss functions and gradient descent optimizers for both models. So both models are going to use this cross entropy, which is binary cross entropy. So we're going to use tf.keras.losses, and we're going to grab the binary cross entropy function from there, and we're going to set log it's to true because we're dealing with probability distributions, and we set that we assign that to a cross entropy variable. So now the discriminator loss, we're going to define a function here for that, and then that's going to quantify how well the discriminator is able to distinguish real images from fakes. So it's going to compare the discriminator's predictions on real images to an array of ones. Because again, if it's a real image, that is going to correspond to a 1, which means it's a real image. And now we're going to compare the discriminator's predictions on fake or generated images to an array of zeros, because we want fake images to be classified or to have an output of 0. So 0 corresponds to generated or fake image, and 1 corresponds to a real image. So let's look at our function here. It's going to take in two parameters, the real output and the fake or generated output, and we're just going to calculate both losses. So the real loss, so we have our cross entropy loss here, binary cross entropy, and we're going to pass in two parameters here, which is what we're going to compare. So we have our real output, which is what we want, and then we're going to create a tensor here. So we're going to call tf.onceLike. So this tf.onceLike, what it's going to do is it's going to grab its input parameter here, the real output here, and it's going to create a tensor of the same shape. So the same shape as the real output, but then in every entry in that tensor is going to be ones, and it's going to compare and minimize the loss, minimize the difference between the real output and 1 and all of those ones. Now for the fake loss, which is the second part of the loss for the discriminator, again cross entropy, but now we want tf.zeroslike, because for the fake, so it's going to take in the fake output as a parameter here, this zeroslike, is going to create again a tensor of the same shape, but now filled with zeros, because now for the fake output, because we want the classification to be 0 for fake, we want to be comparing the fake output tensor to a tensor of zeros, which is of the same shape. So we have those, and the total loss is simply the sum of these two, and we want to minimize the total loss here for the discriminator. So now for the generator, we have a loss as well, so the generator loss. And the generator loss quantifies how well it was able to trick the discriminator, so to speak. So intuitively, if the generator is performing well, then the discriminator will classify the fake images or real or generated images as 1. So here we will compare the discriminator's decisions on the generated images to an array of 1. So it just takes in the fake output, the generator loss, and it's just going to compare to ones, and is going to minimize that, basically the distance or the difference between these two. So the fake output to 1. So we want the fake output to be as close to 1s as possible. And then that means that we have a well-trained generator that is generating essentially real-looking images, which is what we want. So now the discriminator and generator gradient descent optimizers are different because we will train two networks separately. So we just create two variables for those two individually. And we are going to use Atom here. So tf.keras.optimizers, very nice. And we just pull the Atom gradient descent optimizer. And we're going to use the same for both of them. And for the parameter that we're setting here is the learning rate. And we're going to set the learning rate the same for both of them. So now let's go. So once we have that, we have our networks, we have our losses, we have our gradient descent optimizers with our learning rate. Now we want to save our checkpoint. So we're going to create a checkpoint directory here locally, and then checkpoint prefix here. And then we're going to call tf.train.checkpoint, and this is just takes in an arbitrary number of arguments. So we're going to just pass in these 4 arguments. We want to save the optimizers, and then the generator and the discriminator models themselves. So that's what we have in our checkpoint. So now we're going to define the training loop. So we're going to define our hyperparameters. So first, our epochs. So for this example, we just choose epochs to 50, set it to 50 epochs. and we're going to choose the noise dimensions. And as we saw before, just 100 is just what we want as an input to our generator model. And then number of examples to generate, we'll just set it to 16 arbitrarily. And now we are going to create a variable called seed, and we will just reuse this seed so it's easier and visualize our process. So we assign tf.random.normal, so we sample from a normal distribution here as well, sample random numbers, normal distribution. This is the shape that we want for our tensor. So number of examples to generate, so 16, and then by 100 noise dimensions. For each example, we want 100 in that dimension. So now let's go ahead and create our function. So here, and actually in TensorFlow 2, the way we actually build graphs is using tf.function, this @tf.function annotation here on our functions. And so eager execution is turned on by default in TensorFlow 2 and TensorFlow 2. And eager mode is great, but for optimization, and when we're ready to export to production and export our models and put them in embedded devices and or serve them and so on, we want to be able to have the highest performance possible. So here, our TF function will basically trace our functions whenever we put this TF function. So it's like an op that you define in Python to create graphs, and it is faster than eager. In a lot of cases, and these TF functions are polymorphic. So even though you're using Python and the data type that comes in is dynamic, our TF function is going to look at the tensor inputs for a function and basically create a graph, and it's going to ask behind the scenes if we already made the graph compatible with these inputs, and if not, it's going to create a new one. So this is how TensorFlow 2 is creating graphs behind the scenes for us, so they're actually optimized for different data types, which is very, very nice. So here we have our train step function, TF function, and it's going to just take in images, a batch of images for a training step. So we create just a variable called noise here, again sampling from a normal distribution, and we want the dimensions to be the batch size and then the noise dimensions. So that's our tensor. So now we're going to create a context manager here with tf.gradient tape as gen tape, so the generator tape, and then the discriminator tape, because we have two. And this, what it does is to record the operations for our graphs and also record the gradients for these operations. So we have our generated images here, and this is the output of our generator. So we set training to true, and we pass in our noise variable here to our generator, and it's going to output our generated images. So now we have this is the generator, and now for our discriminator, we want to pass in the real images, and again setting training to true because we're training. And now it's going to produce the real output, right? Because these are the real images. And this is a batch that we're passing that we pass in here. And now we also want not only the real output, but the fake output also for the discriminator. And for this, we pass the generated images onto our discriminator. So we have both of our outputs here, real and fake, or generated. So now we want our generator loss here, and it takes in our first of all, we're going to take in our fake output here. So this output, we pass it into our generator, and that's the generator loss. And now we also want the discriminator loss, which is going to take in both the real output and the fake output. And so that's the discriminator loss. So now we basically just get our gradients for the generator, the gradients of the discriminator using our gen tape and this tape that we have here, and just get the gradient on it, and pass in our two parameters, which is the loss, and then the trainable variables from our generator. So our generator and discriminator have learnable parameters or trainable variables, and we're just going to grab those and our loss, and we put that into this gradient function. So we have those, and then we also want the generator optimizer, discriminator optimizer, and we're going to apply the gradients here that we have. So we just zip them up, the gradients, with the trainable variables. Again, feel free actually to pause here and see how this TF function is working and how we're using TF gradient tapes to record our ops, our operations, and our gradients, and then record that. So the next step here is to define a train function that is going to take in our data set, our batch data set, and then the number of epochs. So very standard. So for epochs and the range of epochs, we just record the time here, the start time, see how long it's taking. And then for image batch in the data set, so for each batch in this batch data set, we're going to pass in our image batch into our train step. So this is where it's coming from. This image batch comes in, and then we do that those gradients and losses and so on. So now we just want to display here the images to see as we go during training, and then we also want to generate and save the images, and we have a function here that just generates and saves these images because we want to actually show them. And then, so every 15 epochs, we're going to actually save to our checkpoint, and we're going to go ahead and just print that out. And that's it. So that's just basically how we train. It's very simple. Just go through our epochs, just run the training steps for our batches, and just go ahead and save our output images, and also save the checkpoint every 15 epochs. And also feel free to actually pause here as well to see how this is working. So now here for training the model, we just simply call train. We call this train function that we defined here. And we simply pass our train dataset, batch dataset that we defined before, and the number of epochs. And at the end here, this is what we're going to end up. So we first have noise, and here I can show you real quick how it happens. So initially you see when it's just kind of noise, and then the network during the epochs during training, its learnable parameters are updated, and it gets better and better at creating and generating handwritten MNIST digits. So we have that, and then we just restore the checkpoint, create a GIF. And now we're just going to display an image and just grab the latest. So at epoch 50, we grab that one that we stored locally in our local directory, and that's how it looks. So at 50 epochs, it's not perfect, meaning it hasn't gotten to its ideal point and as far as, well, generating real images, but it's getting there. You see 8, 4, 9, maybe 7, it's getting really good. So you can imagine as you improve and optimize and tune hyperparameters and increase the number of epochs, you can get to a point where you're generating images that look pretty much real. And now you're increasing the total data size of the data that you have, which is pretty amazing to how these networks work. Thank you, Ian Goodfellow, for discovering these networks and helping us here. So, and here at the end, we just simply run this function here, or this code that basically creates a GIF, which is what I showed you here, just so you can see as epochs go by, just how we go from noise to handwritten digits that are being generated by artificial intelligence. Incredible. So yeah, thank you for watching. If you have any questions, thoughts, comment below, and I will see you next time.